To start today, we should review properties of expectation and talk about what you should be able to use and derive, including with the variance formulas as well and their properties. So I've written this down before, but it's worth writing again. Properties of expected value, or just expectation for short. Wrote these down, I think, a week ago. First of all, the simplest property, the expected value of a constant is the constant. Really, it's not a plain old constant. It's not a plain old number. It's a constant random variable. Constant random variable, meaning it's a quantity in a random experiment that always ends up being the same thing with probability 1. There's no other possibility. I don't know, what would be an example? Consider the experiment where I jump in the air and I record the outcome of I either land on the ground or I explode. Okay, feels like a good model is that I will always land on the ground. Okay, X could be what's called an indicator random variable, and it will be 1 if I land on the ground, and it will be 0 if I explode into nothingness. I always land on the ground with probability 1, so X always takes in the value of 1. It's a constant random variable 1, and I would expect it to always have an outcome of 1. My mean value for X would always be 1, would be 1. The expected value of a sum of two random variables. Oh, I got the order wrong again. The expected value of a constant, C, times a random variable. That constant can be factored out. And yes, 3, the expected value of a sum is the sum of the expected values. I think I brought up the bowling example. Just an example in your mind here. You and I, we decide to go bowling together. Not saying it's ever going to happen, but if we did, X would be my score, say, and Y would be your score. Our total score for competing against 2 other people would be X plus Y, and we win if our X plus Y is bigger than their X plus Y. Now, of course, when you bowl, like when you golf, whatever, it's random. You don't know what score you're going to get. You could try to model it. Maybe with a normal distribution, bell-shaped curve, we'll talk about that in chapter 4, which is a little funny because that's continuous, whereas your score in bowling is discrete. And well, what's my mean score over my lifetime as an adult? It's not real great. It's maybe 125 or something. What's yours? Maybe you're a better bowler. Maybe your mean is 170. It should make intuitive sense that the mean of our sum of our scores would be 120 plus 170, 290. To truly verify these means experimentally, you'd have to bowl many, many, many games together, say hundreds and hundreds of games, and compute your averages. Okay? That would be an experimental verification of this. To prove this theoretically, even though it seems intuitive, is actually much harder than you would guess, because the distributions of X and Y could be very different. Maybe mine would be normal. Maybe yours is not really so normal. Skewed distribution, if you've taken stats, like a right skewed distribution. And so how do you deal with those kind of complexities, like when adding your 2 random variables, your 2 random scores? The way to do it is to put it in a different context, multivariable calculus effectively in chapter 5, and we will do that. Even though technically multi is not a prerequisite for this course, it'll be okay. You won't need to know everything for multi, okay? By the way, you can combine these 2 properties effectively and use induction, really, to say that the expected value of a linear combination of random variables. Oh, linear combination, what is this, linear algebra? Is the corresponding linear combination of the expected values of the random variables. You've seen these kinds of properties occur in your mathematical past before. Calculus. if the expected value operator was a derivative operator, and x and y, instead of being random variables, were differentiable functions, this would be saying the derivative of the sum of two functions is the sum of their derivatives. The derivative of a linear combination of functions is the corresponding linear combination of their derivatives. You've done that kind of thing before. Also in linear algebra, if x and y were vectors and E was a linear transformation, maybe not everybody's taking linear algebra, the linear transformation applied to the sum of two vectors is the same as the sum of the output of the linear transformation when you plug in each vector individually. And that generalized to linear combinations in linear algebra. Maybe you haven't had linear algebra. What about the variance? Remember, the variance by definition is the expected value, not of x itself, because that's the mean, but of x minus the mean squared, where mu is our shorthand symbol for the expected value of x, the mean. That's the definition of the variance. It's supposed to be intuitive that it should be somehow a measure of spread. If you've got a random variable that doesn't vary very much, vary, V-A-R-Y, vary, V-E-R-Y, much, like it takes on only two values, say 0 for tails and 1 for heads. The mean for flipping a coin would be, say, 0.5 if you have 0 be tails and 1 be heads, and a probability of heads being 0.5. Sometimes x is 1, sometimes it's 0. 1 minus 0.5 and 0 minus 0.5 are both 0.5, or 0.5 and negative 0.5. We square those, you get 0.25 in both cases. Actually, yeah, that's not very much spread because this takes on, in that case, I guess a constant value. And it still is a positive value. It is a constant random variable in that case. Its expected value is going to be 0.25. Whereas if you've got a random variable x that can take on lots of values, like rolling a die, more values than flipping a coin, 1 through 6, say, and the mean is 3.5, then sometimes x is 1, 2, 3, 4, 5, or 6. In each case, you subtract 3.5 and square it. You're going to get a variability of numbers by chance, and you would expect an expected value that's larger than in the coin flipping case. That's the definition. You should be able to do what I'm about to do on exam 1 to come up with the formula, the shortcut formula, or the computational formula as it's called for the variance. First step is just to use FOIL, your old friend from algebra, to square this to get x squared minus 2 mu x plus mu squared. Now you might ask, can you really square random variables like that are the difference of two quantities? And I guess in this sense, mu would be thought of here in this context as a constant random variable. And the answer is yes, but I'm not going to justify that. So I FOIL there to get this, and now use properties of expectation. These two properties, 2 and 3. Which, by the way, I forgot to mention, I also call these linearity properties. Linearity properties is what I call this. And I should also mention the derivative operator, while it satisfies 2 and 3, does not satisfy 1, right? The derivative of a constant is 0. It's not the constant. So it's kind of like a derivative operator, but it's certainly not the exact same thing. It does share these kinds of properties with derivatives. Use those linearity properties next. So the reason for this equation is going to be linearity. I've got the expected value of a linear combination. 1 times x squared. I said 1 because it's like it's a coefficient of the x squared. Minus 2 mu times x. Plus the constant random variable mu squared. I can write this. And yes, I could write the expected value of mu squared, but that is a constant, so it does equal mu squared. I guess that's property 1 of expectation. Can this be simplified? Yes, it can. Because we know this equals mu, right? Mu and E of x, the expected value of x, are the same thing. So we get the expected value of x squared minus 2 mu squared plus mu squared, which simplifies to the expected value of x squared minus mu squared, which can also be written as the expected value of x squared minus the expected value of x squared. The expected value of x squared minus the expected value of x squared. And unless x is a constant random variable, this is not going to be 0. It's going to be a positive number. Yes, the variance of x does equal this. By the way, the reasons for these equalities are just simplification. Algebra, you might say. Simplification. That's the equation for the variance. Again, like I said last week, the most common mistake here is to think that the variance is just the expected value of x squared and hope that you're done. No, you got to subtract the square of the mean. Don't forget to do that. That's the most common thing to forget. It's so common to forget it. Once in a while, I forget it. Especially when I'm trying to use moment generating functions to compute moments, like the second moment, and then I forget, oh, that's not the same as the variance. I got to remember. And yes, I mentioned this last week too. You could solve this equation for the second moment. There are some times where you might have a problem-solving situation where you know what the mean is, and you know what the variance is, and you are asked for what the second moment is. And so you could use that equation. That's hardly ever done in practice, you might say, but technically it could be done. The standard deviation, the variance is also called sigma squared. Standard deviation, sigma, is the square root of sigma squared, square root of the variance. In other words, the square root of the second moment minus the square of the first moment. That's the standard deviation. We also talked about the 2 standard deviation rule of thumb. These things are numbers. Mu is a number, sigma is a number. In fact, when we get to statistics, we're going to give these things special names. We're going to call them population parameters. In fact, I may even use that terminology even more today with the rest of the topics for today. Population parameters, they're measuring something about a population that you are trying to model. And they are parameters in the sense that they're constants that characterize the model. A mean and a variance and a standard deviation. And yes, there's the 2 standard deviation rule of thumb. Draw a number line here, mark off these numbers. Sigma is thought of as a distance here. Almost all the probability will be within 2 standard deviations of the mean. Now, that's a rule of thumb. It's not a theorem. There's never any theorem that says almost all of something. Actually, that's a little bit of a lie. There's a very advanced area of math called measure theory, where the phrase almost all has a real precise meaning, but not here. So for us, it's a vague rule of thumb. Almost all the probability is within 2 standard deviations of the mean. the probability of being within 2 standard deviations of the mean, that the distance between x and mu is less than or equal to 2 sigma, is quote unquote large, say real close to 1. Of course, it's got to be less than 1. Could be equal to 1, but it's not going to be bigger than 1. Absolute value of a difference is the distance between them. So you're saying, what's the probability that your random variable has a distance to the mean of less than or equal to 2 standard deviations to be in this interval somewhere? It's going to be close to 1, pretty much no matter what your random variable is. Now, there are some technicalities here that you should realize. I'll maybe emphasize a bit more on Thursday and next Tuesday. The mean and the standard deviation actually don't have to exist. There are distributions where the mean and standard deviation, or one or the other, don't exist. Huh? Like if you've got an infinite sum, you're computing the mean using this formula, and all x means an infinite list of x, so it's an infinite sum, and maybe the sum doesn't converge. Maybe it diverges. If this diverges, the mean doesn't exist. How could that possibly happen? We'll talk about that. It actually can happen even in modeling situations, and it might even be an accurate model, real life model. Should also know properties of variance. Properties of variance, abstract properties. You'll find these still in chapter 3 on page 58, called rules of variances. First property is that the variance of a constant is 0. If your random variable is constant, there's no variability. It's always equal to C with 100% chance. Its mean is C. Going back to the definition of the variance, x will always equal mu, so x minus mu will always equal 0. 0 squared is 0. You will get a variance of 0. Second property is that you can factor constants out, kinda. What do I mean by kinda? I mean, you can factor them out, but you have to square them. A little weird, but true. If you take the square root to get the standard deviation, the corresponding property for standard deviations, if you labeled it as sigma sub cx, this would be the square root of the variance of cx, would be the square root of c squared times the variance of x, would be the absolute value of c times the square root of the variance of x. In other words, there would be the absolute value of c times the standard deviation of x. That would be the corresponding property for standard deviations. The square root does go away for the c, but you do technically need absolute values to account for c possibly being negative. Variances and standard deviations can't be negative. And a third property is a linearity property with respect to summation. The variance of a sum is the sum of the variances, but this is a very big but. The random variables can't be any old random variables for this to be true. It is true in a very important special case if the random variables x and y are independent. What is independent random variables? We haven't said. Chapter 2, we talked about independent events. A and B were independent events if the conditional probability of A given B is the same as the ordinary probability of A. Remember that? And also vice versa if you switch around the A and the B. It also led to the multiplication rule for independent events. The probability of A intersect B the probability of A times the probability of B when A and B are independent. But what are independent random variables? We haven't said. It's a chapter 5 thing, where multivariable calculus is relevant again. Intuitively, you might think of these as being unrelated. Now, if you and I were going bowling together, it's possible our scores are not independent, because maybe if we're real competitive, am I competitive? Sometimes. If we're real competitive and we see that, and I see that you're doing well, it's going to motivate me to try extra hard. And maybe I'll do better. Or maybe I'll be really demoralized and I'm just going to throw it and get a gutter ball every time, right? So in that case, it wouldn't be independent. But if we were doing our best and bowling in different bowling alleys and not communicating, then it would seem reasonable that our scores are independent, unrelated to each other. Your score or knowledge of your score doesn't affect what my score is going to be, and vice versa. If they're not independent, this is not true, it turns out. And by the way, the corresponding property for standard deviations, if you wrote it with subscript notation, would be this. And this cannot be simplified any further. Once again, if X and Y are independent. The standard deviation of X plus Y is the square root of the variance plus of X plus the variance Y, and that cannot be simplified. It's not equal to, in any situation, the sum of the standard deviations, okay? When I teach statistical analysis students to business students, they always think this is true. They think these things are equal. They think the square root of a sum of two numbers is the sum of their square roots. No. Sorry. Just try an example. The square root of 4 plus 9 is the square root of 13. Is not equal to the square root of 4 plus the square root of 9. Oops. Which is 2 plus 3 is 5, right? No. Okay, so don't, your math, computer science, engineering majors, no, don't do that. Not equal. Okay. These properties are very important, okay? You do want to get them in your soul in working through this class. We will need these at various points during the semester. Can I clarify anything? If these are not equal, then they're not independent? Yeah, that would be true. It's not the definition of not being independent. This is not the definition of independence, but it's if they are independent, then this is true. Is there a formula for this variance? If they're not independent, there actually is, but it involves another concept called a correlation.